So it's my pleasure to welcome Professor Amin Benzaga, who is the General Dynamics Professor of Aerospace Engineering at Texas A&M. And he joined Texas A&M in 2004. He did his PhD from Means Paritech in 2000. And he's currently the director of the Test Center for Intelligent Multifunctional Materials and Structures, and holds also is a faculty at the Department of Material Science and Engineering there. So Professor Benzaga has received a lot of awards and so on. I'll not go into all those, but his contributions to ductile fracture, mechanics of ductile fracture is something that's very noteworthy, and that has caught the attention of everybody. And it includes both excellent experimental work on the subject as well as theoretical developments that have had far-reaching impact. So with that, I would give the floor to Amin. Welcome, Amin. So I will disappear and I will reappear at the end. I kind of feel like God. I can appear, reappear. I can give you voice. I can take away your voice. So I enjoy that. Okay. Floor is yours.
All right. Thank you very much, Sumit, for this kind introduction. I won't be talking about cracks at all today, or voids or anything. As this is a talk essentially about education in structural mechanics, a field which in many engineering programs may be the very first encounter of students with deformable bodies. And so the talk is really a critical discussion of so-called strength of materials. I'll define what I mean precisely by strength of materials and structural mechanics a bit later. It's a discussion, a critical discussion of that. It's in traits, it's in coherence. Not much in the results that are typically obtained, but in the way in which they are obtained, and therefore in the way that the subject is very often taught. And so, this will naturally lead us to the utterly dichotomized nature of this field of SOM. And in order to understand this poor state of affairs, this character actually bestows upon the SOM as being somewhat boring, let's admit it. And to understand this poor state of affairs, one is either compelled to admit that parent fields, continuum, solid mechanics, elasticity, and maybe even mechanics is equally boring, or believe, as I do, that this is a field that has a long history, and that we have given way to excessively utilitarian teaching of it. And so something ought to be done about that, I believe, to elevate the field. Now, this does not say why this giant name is in the title, but this is a brief outline of the talk. I'll provide a rationale for the title first, and then mention specifically the motivation, although I've already touched upon that a little bit, of why this talk. I'll give some background, mostly about terminology, and make sure that we are on the same page. And then dwell a little bit longer on what I call the incoherence of strength of materials, through a couple of examples. Reflect on how we got here, so provide a historical perspective through some inductive reasoning, really. In passing, describe what I believe is central to, what ought to be central to the field, which is the Saint-Venant type of formulations. And then the last 4 or 5 slides, I'll present some educational principles that are dear to me, settle on a couple of core propositions that will be natural consequences of the whole talk, specify the proposal, and close with some remarks. An old acquaintance of mine named Ricardo told me once Puccini killed opera. And the little I knew about opera was that Puccini was one of the great masters of the early 20th century. And so I found the statement a bit condescending. And so I inquired. And what, he told me many things. Ricardo was the kindest, nicest person you could have come around. He had mentioned many things, but what registered with me was that his operas were often difficult, as in unnecessarily difficult. Perhaps one example of that is in his famous piece, Tosca, when he has his soprano yell and scream so much just before the landmark or the highlight piece of the whole opera, the Vici d'Arte. And so many sopranos, if not in public, have confessed in private that this was very difficult to be yelling and screaming so much just before an important piece. And there are many other things that typically are said, whether people agree with them or not, of Puccini as being unsophisticated or catering to the needs of, or trying to please his audience, and seeking to be popular. Now, sometimes also we may hear that, so-and-so has killed the field, right? In the sense that they have solved all problems. Clearly, this is not what I mean here for Timoshenko, because at his time, the field of structural mechanics, many problems had already been solved, and I don't even know that he refined much of that. But that, Stephen Timoshenko does not need an introduction. He's a giant in the field of mechanics. He has contributed in ways that remain unparalleled at the time, where the center of gravity of mechanics and sciences in general was, transitioning from Europe. And he has, in particular, for the interest of this talk, for the purposes of this talk, worked very diligently to make this field of strength and materials accessible to the widest audience possible, to the average student. This may be the thing that is both commendable and precisely the point of criticism here. And so in order to understand clearly is, the main thesis of the talk, so to speak, I'll have to go through some background and trace the history back and have you at least accept the premise that the state of affairs in terms of teaching this field is not what it should be, and then connect that with Timoshenko's responsibility to it. Otherwise, there is no case to make. So the real motivation really is about is a reflection on how we educate engineers in this field of structural mechanics. There are many things that can be said. I won't be too long, but one of them perhaps I would pick up on is to narrow the gap between undergraduate and graduate education in mechanics in general. But from an epistemological perspective also, if most people, everybody essentially is familiar with so-called Euler-Bernoulli beam theory. Some people are familiar with Timoshenko's beam theory. But if you throw the phrase Saint-Venant beam theory, it's very little known. People know eventually about the Saint-Venant principle. This is something you find essentially everywhere, but the exposition of it is not to the level it deserves. So interestingly, if you look through some dates in there, in Euler-Bernoulli, we are talking about the mid-18th century. Timoshenko's beam theory is from the 1920s, but Saint-Venant's work was really in the mid-1850s, right? So there is also a bit of an anachronism here. The first two theories are really approximate theories. The last one is an exact theory for what it set out to address. And so it's legitimate to ask, why 70 years after exact solutions have been made available, somebody would come up with an approximate theory. It's for at least legitimate to ask the question. But The aims of the talk and what I've been doing in the past couple of years is really try to elevate education in structural mechanics. But people may or may not agree with my premises, but that's the whole purpose of this conversation. And also to make Saint-Venant's theory more accessible and more known. So what do I mean by these terms? Then I don't mean to be overly precise here, extent of becoming obscure, but I think you may define structural mechanics as this branch of solid mechanics that's concerned with structural elements, right? Beams, plates, and shells, and assemblages thereof, right? Trusses, frames, ossuatures, and so on. Oops, what's happening? Strength of materials, on the other hand, in its pure sense, may be a broader field concerned with determining the load-bearing capacity of structural elements, usually limited to bars and beams, but not necessarily. Theory of elasticity is a branch of solid mechanics concerned with the elastic response of bodies, right? And you'll come across also the term mechanics of materials, which at the undergraduate level is used as a surrogate of strength of materials, essentially. From where I came from, it referred mostly to a graduate standing subject, so one has to be careful of the terms. But so here, for the purposes of this talk at least, when I refer to structural mechanics, I mean that branch of solid mechanics concerned with structural elements using a theory of elasticity approach, as opposed to redefine strength of materials, because that's how I understand SOM books, as the branch of solid mechanics concerned with the same thing, but using approximations. Okay, so when I refer to SOM subsequently, that's what I have in mind. And it's perhaps edifying from the outset to typify the differences in the approaches to the subject. And, two instructors teaching the same subject, one adopting an SOM approach versus structural mechanics with a theory of elasticity approach. In the simplest case of, say, a bar in tension of compression, an arbitrary cross-section. If you're typically the SOM approach would basically, very quickly settle on discussing the average normal stress on the cross-section. Don't even know why they talk about average. It's force divided by the cross-sectional area. Some books eventually elaborate on Saint-Venant principle, and it's commendable. Hibbler is the case very early on in tension. Although the statement there, I'm not sure it's quite correct, because he talks about a point load and then compares that with 2 point loads with half the magnitude, right? Already going into slippery terrain, I think. But the difference in approach on the other, is really how the two instructors would reflect on how the end loads are applied. You'll see immediately whether you're adopting a strength of materials versus theory of elasticity approach. The other issue is what is said about the lateral surfaces. Very often, if not always, SOM books, you're just brushed over, right? So this typifies, and then I'll get to this obviously later on when I talk about the Saint-Venant problem. So this leads me to directly the core of the criticism, essentially, because if people do not agree with my premise, so there is no case. What they call the incoherence of the strength of materials as presented in textbooks and widely taught. And I picked just a couple of examples here to make the point. It is fair to say that the Euler-Bernoulli beam theory is widely known, widely used. If you examine, it's not always presented this way, but it's typical for people to assume that cross-sections do not deform, they're rigid, and that they remain plane after deformation and perpendicular to the deformed axis. Then, you look at the axial displacement because of the results solely because of the rotation of the cross-section, treated as rigid rotation, basically. This is presented in the simplest case, right? Linear in one of the coordinates in plane of the cross-section. And because of assumption A3, you can relate that to the slope of the axis. Vg here refers to the deflection in the y direction of the centroid. And you use kinematics and Hooke's law in this simple case to infer that stress must be linear in the position y. And then from the moment traction averaging relationship, you get this relationship. And so therefore, differentiating one, equating it to 2 with due account of 3, you get the famous deflection or curvature moment relationship. Okay. Now, if I'm a student, I'm inevitably left with the impression that the assumptions made are essential to obtaining the final result. So consider relaxing the first assumption and allowing the cross-section to deform in its plane, right? For example, you could pick that the lateral displacement of the V is given by some arbitrary polynomial function degree 1 in the axial position x times some arbitrary function of y and z, the in-plane coordinates, plus this term here. I'm having in mind the sort of cantilever beam time, right? Then clearly, if you take the second derivative of the deflection v with respect to x, because this is a polynomial of degree 1, this term disappears, and you end up with the same equation, essentially, regardless of what you assume of the axial displacement u. Likewise, if now you relax A2, that is, you allow for warping in a sense, right? You don't accept that plane sections remain plane, and so therefore in this case you must have relaxed also A3, and possibly the axial displacement would have some dependence upon the in-plane coordinates that is not commensurate simply with the first term, but it can be another term here, function of y and z. You take the derivative with respect to x, because this function does not depend on x, it disappears. And so again, by invoking Hooke's law and the kinematics, you end up at least with this equation remaining valid. And if in addition you assume that the rotation is a separable function of in-plane and out-of-plane coordinates, then you can show that the moment curvature equation is valid as well, regardless of the cross-section in plane deformability. So what are the implications of this? What I'm showing you here, and again, for simplicity, I'm absorbing now what I called A3 into A2, right? That Euler beam theory tells you rigid sections and plane sections remain plane, implies proposition B, which is the curvature moment relation, right? But in the previous slide, I've just shown you that you could relax A1 or A2 separately and yet obtain the same result. So, if I call proposition A the conjunction of both A1 and A2, what I'm saying is that both A and non-A imply B. What does that tell you? That A and non-A are essentially not important to obtaining the final result. Or if you want, the final equation is valid in spite of plane sections remaining plane or being rigid or not. And so there is an inherent fallacy, and while it's harmless at the end from the purely utilitarian point of view, because at the end of the day, it's the main equation that probably begin using in studying plane bending problems, which are very important in this field. Nevertheless, the student is left with the impression from the logical standpoint that the assumptions were essential. And this is deeply incoherent. Obviously, the theory violates equilibrium. So getting to a final result that's true from starting from something that's right or wrong doesn't matter. Logically, the implication is correct, it's true. Another example is the shear formula. Well, now, of course, you have to invoke equilibrium, right? This was developed by Juravsky in the context of a rectangular section. And so if you assume that the you know the shear lines, right? The orientation of the shear lines. That basically, the shear stress is parallel to the applied shear force, and that in addition, it's uniform across the width at a given height. The magnitude may vary with the height, but across the given width at a given height, you take it to be uniform. Then I'm not showing the details here. You arrive this expression for the average shear stress, which is taken to be constant anyways, across the width, as the applied shear divided by the width times the second moment of the area. And then here you have this height dependent quantity, which is the first moment of the domain shown gray here. Very useful formula in practice. People don't bother much about the sign. That's what SOM books tell you. I put it here for reasons that I can get at the end. But and, you know, the SOM textbooks typically are going to have a disclaimer saying that, you know, be careful, this does not apply to wide flange beams and whatnot. For example, in the latest edition of the famous book on mechanics of materials by Gunnar Gier, they say common error is to apply the formula outside of its domain of application. Incidentally, you know, Timoshenko in several of his books refers to experiments that show that the formula works well, and very often he doesn't say what experiments he's talking about, and many other more modern textbooks do essentially the same. We don't know what experiments they're referring to. Now that we know from the exact solution, of course, that the shear tractions have to be parallel to the surfaces everywhere, but essentially the exact solution gives credence to the assumptions made by Juravsky, right? I mean, there's a slight gradient here, but it's nice. But so when does the shear formula work? You know, obviously the textbooks, the SOM textbooks are going to discuss the rectangular section where it was derived by Juravsky. Then typically they would go into the circular section. That's an interesting case because of the curvature. You know, the higher you go from the center line, the more, of course, the shear stress becomes less and less parallel to the applied shear force. So you think you are departing from one of the main assumptions of the derivation, but yet, you know, it still works very well. And textbooks are gonna congratulate the formula for getting errors as small as 10%, 13, whatever. It's very small. They're gonna warn you against cases of wide flange beams. For example, I sections is typically what's given. These are the three cases that are commonly given in order, just like in Timoshenko's very first book on strong materials. And they will tell you, on the wide flanges, the top and bottom have to be careful. But you know what? At the end of the day, it doesn't matter because the maximum shear stress is the centroid here and the central web. And so for design, that's what matters. You have to be careful about how you design the connections here to avoid stress concentrations and whatnot. But it doesn't matter. So, but the student at the end of the day does not really know why it works. When errors are thrown at the student in percent, I think something like 15% sometimes is given for rectangulars for a square section or something like that. You know, they refer to some distant theory of velocity. You know, it's very interesting. All these books, all of a sudden, you know, theory of velocity appears as a sort of magical distant theory that we invoke to discuss limitations and measure errors. But the student does not really know what we're talking about. So how the error is measured is never stated. We just have to admit it, basically. And in fact, you know, the authors get too excited, so they fall into the confirmation bias because I may have missed it, but most books I've read, they talk about errors up to 15%, maybe 20%, and you know, they give some warning about wide flange beams, but it stops there, right? Now, there are many cases when the shear formula does not work. And one need not go much farther than the rectangular cross-section to illustrate that, right? So if you begin to make it a bit wider, you know, use the B over A ratio larger than 1, you begin to see some gradients building in, but still okay, I think. And the question is, what happens if you get into wider and wider beams? So the thing begins to look more like a plate in a sense. But what you get is that very strong gradients emerge, both in magnitude and in direction. And they do for values of the aspect ratio as large as 4, for which the maximum shear stress in the direction of application of the shear force is as high as twice this value, which is basically the average value in the center line in the Juravsky formula, the shear formula. And if you use a factor of 15, as shown here, this factor becomes 5. So you're talking about 200% error, 500% error. What sort of a theory is this? Interestingly, for the case shown here of a large aspect ratio, even the direction of the maximum becomes now not in the direction of the applied shear force, but perpendicular to it. And I'm sketching that in here. You see, first of all, the huge gradient for the tau xy, the shear stress in the direction of application of the force at the center line. But in addition to that, above this aspect ratio, the maximum shear stress shifts from this point here, on the surface of the center line, to near the corners in this direction. Just a huge gradient. It's a very interesting problem. And Eric Eisner had sort of pointed this out in a paper in 1946. One can only imagine why he was interested in this limit. What do SOM books say about that? Nothing. In quantitatively nothing, right? They may refer to be careful not to use it when it's not applied, but they say nothing about it. And obviously, this is all in Saint-Venant solution that Eisner had basically the numerical application of the results that were published in 1855 by Saint-Venant. And I could go on and on. I just decided not to dwell too much into that, but one can talk also about Timoshenko beam theory. I mean, because Euler-Bernoulli beam theory violates equilibrium, you get some inconsistencies. So you want to correct that by adding another inconsistency of the so-called shear coefficient, essentially violate kinematics unless you interpret things in an average sense. But I don't have time here to get into this, but it is incoherent. Nearly every topic or subtopic of strength of materials as taught nowadays has some inconsistencies in it. And we tend to overly justify that by the principle of simplicity and the math level that is accessible to students and so on and so forth. I mean, to understand this state, I think we have to reflect back and see how the field has evolved. And there are two classical, historical accounts of the field of strength and materials. Perhaps the very first one in our profession has been written by Adhémar Barré de Saint-Venant in his famous Historique abrégé, which was basically, just before this annotated version of Navier's Résumé des leçons. But the most famous, I think, book on the subject is the one written by no less than Timoshenko, which essentially doubled the volume. I mean, you can see that as essentially a translation of Saint-Venant's Historique abrégé, augmented with what happened between 1860 to, say, 1950, as enough development had happened in that century. I'd like to point your attention also to this more recent, excellent book by someone who's not really academics, but construction engineer. Very, very good book of theory of structures and strength of materials, elasticity. I bought this book about a year ago, and then in preparing for this talk, I discovered there was an edition in 2018 that is now 1,200 pages long. So it's a fantastic resource. Reading through these long historical accounts, is not enough to understand why we've been teaching the field the way it is, but at least not explicitly. But if one, by some sort of inductive reasoning, can come to the thesis I would like to present to you, and we'll see. It's fair to say that the field of strength and materials in the 1800s was, crystallized in the Résumé des leçons by Navier. Okay, in fact, you could argue that 100 years later, Timoshenko's book is essentially, give or take, the same thing, that same content and same logic and so on. So there were the first edition that was typed or printed by Navier was in 1826. There was another edition in 1833. I can't remember exactly when Navier passed away. This is not the dates of his life. This is the dates of publication of the three editions. The most famous is the 1864 one, which is annotated by Saint-Venant. And so what's interesting, the whole book is about 400 pages long, but the section of interest that was edited by Saint-Venant and kept in the third edition was about 80 pages long in the 1826 version, 120 pages long. And then in Saint-Venant's edition is over 850 pages long. And the whole book is about 1,200 pages if you count also the Historique abrégé, the history of the field. If you read the fine print here, you see that when Saint-Venant edited this, he was already retired. At some point, Timoshenko says, oh, Saint-Venant did not particularly push for teaching the field in a different way. He was already retired. In his, so I'm gonna be quoting extensively. I've studied in particular Timoshenko's books and on strength and materials and his history. So I'm gonna be quoting extensively from that to settle on the thesis I'll make. He recognizes, for instance, that Saint-Venant's publications, by that he means Saint-Venant's edition of Navier's Résumé des leçons in 1864, but also his translation and edition of Klebsch's book on elasticity in 1883, which tripled the initial text of Klebsch. So clearly, as he states, without a doubt, he found them to be the most important books in the history of the field, and that Saint-Venant's work and memoirs have had tremendous impact in introducing the fundamental equations of theory of elasticity that essentially settled with Saint-Venant, right, into SOM books, and that Saint-Venant worked himself toward that, okay, in that direction. Now, in 1930, the first edition of a book by Timoshenko himself on strength and materials appeared. Now, it does appear that he had authored prior versions in Russian before that. And so this is most likely a sort of elaboration and translation of his earlier notes. In reading through the preface of the various editions, you clearly understand that he was interested in something that's practical, simple, easy, right? And that is commensurate with what he viewed then as the usual math level of students, which is all fine, but it remains unspecified really what he meant by the usual math level of the student at the time. In fact, he had that in 2 volumes. In the second edition, something that he deemed of more advanced character was removed from part 1 and moved to part 2. Later on in the third edition, he brought in some other things about curved bars and so on. But clearly from this book, written about a century ago, right? Timoshenko had deliberately avoided to adopt a theory of elasticity approach to education to SOM. Okay? In reading through some of his remarks in the history, and I'm quoting here, so the 1953 edition with specific page numbers for ease of reference. In discussing, for instance, the German school, right? Grashoff, for instance, had published a book. The actual date is 1878, I think, where he, following Saint-Venant's spirit, introduced the fundamental equations of theory of elasticity in teaching strength and materials. Then Timoshenko deemed the book as not popular with practical engineers, too difficult, and so on and so forth. So we can sense already sort of how he feels about the matter. And the same is essentially said of Winkler, who had tried something similar. I think Winkler started at Dresden and then was at Berlin. And then he settles that basically these attempts by Grashoff at Karlsruhe and others in Russian engineering schools, he did not mention specifically, proved too difficult for the average students. And so he thought back then that they were gradually discontinued, which was by and large true, but not everywhere. That he did not seem to be clear on. But we sense how he felt about the matter. Now, on the French school, he says, although Navier himself had developed the fundamental equations, they were not complete, right, by then, but anyways, he did not present in his course the theory of elasticity. So he's saying that Navier basically kept teaching strength of materials in a simple way. A similar statement may be found somewhere else about Bresse. And again, I've quoted this before from Saint-Venant. And then he comes back again to Grashoff and Winkler, who had tried to teach the subject differently, but that this method of presenting SOM has since fallen into disuse. And it is the custom now, at his time, 1953, to teach the subject from a more elementary standpoint. The custom now. Now, this is, of course, over 20 years after he authored the book, it became very popular already at his time. Timoshenko makes some interesting remarks about the methods, although not, discussing deeply the pedagogical aspects and didactic approaches. But for instance, Grashoff seldom uses illustrations and figures. He makes a point about Winkler's style as being terse, not easy to read, and so on and so forth, and making it too difficult. In fact, on the other hand, he praises Föppel, for example, who came after them, who has deliberately not used or followed their footsteps and preferred to teach SOM in elementary way. He does know, though, that in Föppel's book, he does present the equations of theory of elasticity at the end, which none of modern SOM books do, I think. But anyways, he also knows that Saint-Venant was a bit different. Anybody who has read Saint-Venant, I have read even his papers from 1853, presented in 1853 before the French Academy of Sciences, published 2 years later. His paper is about 400 pages long, okay, and the second one is over 100 pages long on bending. Saint-Venant is clearly put serious effort on didactic aspects. He was a fantastic researcher, to me, unequal, both in his time and I would reckon even after him. Deep intellect, technical prowess that was unparalleled at the time, and yet very much concerned about presenting the subject with various declensions, explaining things in various ways, adding illustrations at a time where we did not have the same drawing capabilities we have nowadays and tools. So in summary of this inductive exercise, trying to extract, of course, if I were a journalist today and Timoshenko was still alive, I would just sit down with him and ask him, why did you make those choices and so on. I don't have that luxury. So I had to reason by induction there, reading through the qualitative statements he made about previous attempts at teaching the subject and the choices he has made himself. So clearly it comes from this that Timoshenko was fully aware that Saint-Venant worked towards a theory of elasticity approach to strength of materials, that Grashoff and Winkler in Germany made similar attempts. He recognized the issues of terse style and excessive abstraction in some of the German books. He noted Saint-Venant's didactic efforts. Clearly, he had some appreciation of what the average level of a student in math was at the time when he started at the University of Michigan and later in Stanford, but it's not very clear what is meant by that. And in his 1930 book and subsequent editions, he avoided deliberately a theory of elasticity approach. wanted it to be practical, simple, easy to read and understand. And clearly in reading between the lines, I think he believed that both Navier and Bresse would do exactly the same thing. He did not seem to be aware of the developments that happened in France, particularly at École des Ponts. Okay, École des Ponts is the place where this field essentially gelled, developed, and was crystallized. What happened everywhere else is a periphery. In his history, which is written in 1953, he doesn't talk about what has been done at École des Ponts after 1880. Although he mentions many, many professors there in the 1800s. But, you know, this by itself merits to be written up someday, because even in the 1,200 pages of Courer's latest edition, it's not something that's mentioned, discovered something, but I won't get into the details in the interest of time. So anyway, since then, you know, this is the third edition of Timoshenko's book that appeared in 1955, again in two parts, an elementary and advanced part. And then this has morphed into other versions, right? The name change from strength of materials to mechanics of materials with Gear and Timoshenko, up to whatever edition, I don't know, maybe the sixth, and became only Gear. And the latest is in 2018 by Goodnow and Gear. And clearly, when you look at, and I have not listed here everything, there are many other books. Clearly, many of our colleagues throughout the past 70 years or so tried to incorporate changes in some ways, in various capacities. I must say that the most liberal and most progressive ones have been perhaps in the field of aerospace engineering. It does not have the same sort of inertia of a traditional field of civil engineering, where the whole field essentially, you know, started. But I would qualify, and I don't have time to get into the details, as the most progressive of these efforts being timid and not being brave enough in adopting you know, a holistic approach to the subject. So instead of going and giving examples from a variety of things that written by colleagues, and I don't want to get into this, I'd like to, what remains here of time, go through some concepts and key results from, say, beam theory, right? That I think we all aim or want to teach, and see how well basically an SOM approach fares in discussing such things. And so I'm color coding this by saying, you know, if it's red, it means it's not covered at all. And if it's blue, it's not covered well. Okay? So in my view, you know, a beam is this, what maybe Jerry Erickson would call a rod. So to me, it doesn't matter what you call it, it's the definition that matters, right? And it's not always clear in books that, you know, people talk about beams immediately as straight objects, right? So restricting really the scope immensely, as if structures are not concerned with arches and cables and bolts and rings and things like that, and assemblages of things, right? There is very little geometry done on the subject. I like to do this very early on in the semester when I teach the course, especially for this general definition of a rod. I think everybody defines eventually what the principal frame of inertia, but very few define the Freinet frame, the mobile frame associated with the centroidal axis. And clearly this notion of a built-in twist or washout angle is not essential, but it's not defined. I mean, in aerospace engineering is important because the washout angle is something that typically is used to design against stall, right? Internal resultance is an important concept. I don't like how the so-called sign convention is introduced, tying it to a set of coordinate systems and so on. There's absolutely no need for that. Differential equations of beam equilibrium, obviously everybody covers that, but mostly for straight beams. And in vector form, they're very simple, regardless of the double curvature of the median line. Because at the end of the day, these are differential equations, so you reason on a differential slice, which you can always consider as prismatic. So, but nevertheless, people don't typically cover that. Of course, the projection of the equations on either the principal frame of inertia or the Frenet frame of the median line can be quite complicated if you account for the torsion, curvature, and the washout angle. I think an important concept also in this field is to elaborate and take the time at the beginning, at the middle, at the end of the course of how end loads are applied. It has to do with boundary conditions and so on and so forth, right? I mean, and I gather that Saint-Venant principle is mentioned sometimes, but not very well presented. To me, an essential concept of structural mechanics is to recognize that the Saint-Venant problem is like the DNA of the field. And the course can be and ought to be designed in a way that you have a pedagogically designed sequence of Saint-Venant problems. And also, the concept of a beam admitting a median plane is not mentioned. Most books dwell directly into symmetric sections or asymmetric. And sometimes they make the coverage unnecessarily difficult, like working in arbitrary axes. It's total waste of time. One should work in principal axis of inertia. Other things that, for example, in going from solid sections to thin wall sections, which is important in lightweight structures, the field is dichotomized. So you have a set of derivations for this, and then all of a sudden we get into Brett way of doing things. But it seems like these theorems of flux and circulation of shear tractions are not very well known. And to me, they're essential in operating a seamless transition between the theory of solid sections and the theory of thin wall sections. And while people can do away with that by reinventing the wheel and drawing rather complex and cumbersome free body diagrams and whatnot, many, even the most advanced books, don't have an incomplete coverage of the subject of thin wall sections. For example, Grandin et al. Just doesn't deal with transverse shearing of multi-cell sections. So random selection of topics is a very important topic, just as important, if not more important than open sections. Of course, it's more complicated, it's more difficult, but it's needed. And I can go on, but I think I'm running a bit late here. It's never too late to show a picture of the Saint-Venant. But like I said, it is important to describe the Saint-Venant problem. For every type of loading considered, here illustrated in the case of torsion, which is the one that is actually SOM books have retained to various degrees, but most of them don't get into beyond the circular case, and just refer again to it as a distant theory and talk about warping. Some advanced books like do cover this, Donaldson's and Megson and Craig and Bouchot and others. I think it is important to deal with this, even in the context of a simple bar. Okay. Oftentimes, Timoshenko himself writes that Saint-Venant only solved a few problems, a few cross sections, and other social. I mean, there's an infinite number of cross-sectional shapes. Nobody can solve an infinite amount of problems. And epistemologically speaking, the main contribution of Saint-Venant is not to solve explicitly an infinite set of problems, but to have tackled in such an elegant and definitive way a double infinity of problems, because you have an infinite way in which you can consider shapes of cross-sections, but also an infinite ways of applying the end loads. But in teaching, one does not need to get into, at the graduate standing, this can be taught at a different level. But nothing prevents the instructor at the undergraduate level of specifying certain end fractions and then reflecting upon that in dealing with what they call here the long wavelength. This is not a very precise term, or the far field solution, as opposed to the near field, near where boundary conditions are applied. And I think it's important to illustrate with students that the idea is to transform the problem into a two-dimensional problem that can either be solved analytically in some cases, or using numerical methods, but much simpler than the full 3D problem. Or in certain cases, admittedly, Saint-Venant did not do that, but later on, we can infer that from there, using those shear and attraction, circulation, and flux theorems transformed into a set of algebraic equations. So, there are many key results of beam theory that I fault SOM books for not discussing. So everybody is going to talk about plane structures remaining plane in pure bending, right? Symmetry argument eventually can take you a long way. It's just 5-10 minutes coverage. But the result is true regardless of the shape of the cross-section. They don't show that. I'm not going to go through the details, but that the deflection due to transverse shear is negligible compared to that due to bending. Again, we either have the student admit it or not even talk about it. Admittedly, from a purely utilitarian point of view, since it's negligible, who cares? But this is education, not preparing students for skills that their first employer will need. Again, I've discussed the fallacy behind the derivations of the Euler-Bernoulli deflection equation. There are many other things. Warping occurs under general bending. This is typically stated in books, but it's not always covered, and it's not shown because it doesn't deal with the Saint-Venant problem explicitly. The shear formula, which I call the Brett equation, this is a liberal sort of disposition with the terminology, simply because Brett was really the first one to reason on arbitrary contours in the cross section of a beam, and think about the circulation and flux of a shear traction vector across or along such a curve. And so I think one can attribute that to him. We can show it to remain valid and why it works for rectangular bars, things that SOM books do not get into. One can get into more things in similar things in torsion. You'll see less red here probably because torsion is a subject, I think, from which people have extracted from Saint-Venant solutions more, but still there is no proofs that are given for why non-circular sections always warp, and how such an imperceptible warping can still have a large influence with numerical applications and things like that. Of course, some SOM books are that like formulas. Someone may mention this approximate equation by Saint-Venant. Don't quote me on the date. I'm not sure of the. I know it was in the 1870s. In thin-walled sections, typically, what's covered is the case of a simple closed tube. Eventually, some more advanced books are going to cover the multi-cell. But there are some rather dubious proofs are given when people write that the torque is the sum of the torques applied at the cells. This is not very well defined, right? It's very important to realize that only the shear flows in the external walls appear in that equation, not the shear flows in the internal walls or the webs, okay? And so the formula is not as trivial as one might think. As for the simple open tube, either it's not covered or is dismissed because not important in practice, maybe, right? But one can argue that there are situations where you need to know about that case. And since the case of rectangular sections, the Saint-Venant solution is not developed, so you cannot really deal with the asymptotics in that case. Likewise, for bending in thin-walled sections, things are proven again ad hoc, and very rarely will you see the case of multi-cell cross sections covered. And that's precisely because the authors have not set themselves on a trajectory to show such things. It becomes very cumbersome to use the same reasonings with, on dealing with the axial equilibrium in inferring something about the shear flow in the cross section. The view brought by Brett, I think, you can just reason on the shears and viewed from the cross section very elegantly and obtain the center equation, the key equations. Again, I'm not going to get into the details of that, but in closing, I have last 4 slides here. So what can we do about this? Some principles I would like to just try on people here that are dear to me. The worst enemy, I think, of an instructor is his familiarity with the subject. I think we should not forget that this is a field that, even giants have made mistakes. I mean, what Saint-Venant used to refer to as l'ancienne théorie, the old theory of Coulomb, I mean, on torsion. Navier also bought into Euler, and even Cauchy had some errors in some of his treatments of the subject. So students deserve serious didactic efforts that are aimed at teaching what is needed, not what is simple, right? Very often people say, well, okay, they invoke principle of simplicity. This is too complicated, theory of elasticity. And I'm not sure they're invoking the, true statement of principle of simplicity rather than simplicity bias that, assumes to be true that which we know to be true and seek the simplest way of showing it even if it's fallacious. I think simplicity implies compressibility of knowledge. And that when you have a field that is so inherently analytical as mechanics in general, or structural mechanics in particular, one has to reflect on the regularity of patterns in the things to be taught. Because if there is regularity, then there is compressibility, and that aids in memorizing better than teaching a dichotomized set of topics. Alan Needleman, my mentor and colleague now at Texas A&M, has always told me, in writing a research paper, aim to write it as a story. By way of extension, I like to teach a course as a story rather than a juxtaposition of disjointed pieces. But that requires that some unification of subject, not dichotomization. And in that, I view the Saint-Venant problem as really the DNA of structural mechanics. It really is the enabler of such a teaching methodology. And of course, one is always find oneself in the middle of, what's teaching students skills versus teaching them fundamentals. And it's not one or the other, they have to go together. But I like to quote Edouard Herriot, former French prime minister from the 1800s. He says that culture is what remains when everything else is forgotten. If we teach a subject that's unified, where we compress information in a way that is based on regularity of patterns, then that settles deeper in memory, and therefore, it helps with retention a lot better than stuffing. And perhaps the most important of all principles here in this context, I truly believe that what was cutting edge in research 170 years ago, that is Saint-Venant's memoirs on torsion and bending, and has had a profound impact, there is no question about that, on mechanics, should constitute canonical knowledge. By that, I mean something that ought to figure, at the center of undergraduate textbooks, not some distant thing that eventually is tackled in graduate textbooks, which I don't even know that we're teaching that properly at the graduate level anymore. I think CNM at Nasser was saying in a meeting 10 years ago that polling people in the room how many are teaching theory of elasticity in their graduate programs? And that's a different story. So my core proposition is that Timoshenko, who was such a giant in the field, has impacted education in mechanics in the United States in particular, by way of extension worldwide, but particularly undergraduate education also, and has made educational choices that have had profound impact on how the field has evolved. He has set a very hard and strong initial condition that has limited the way the field has evolved. Now, did he expect the success of that approach at the time? Did he fall victim, in a sense, to that success and willingly did not want to depart from it, even when he knew that somewhere else there were other pedagogical approaches to it? Did he actually make that choice, or was it the choice imposed upon him by the institution where he operated? I don't know. He was fully aware of the deficiencies of previous efforts by Grashoff and company. Did he really make any effort to alleviate the deficiencies? Did he expect that such an introductory course would be followed by a more advanced course at the undergraduate level? Clearly, this is not the case nowadays. And I'm not sure if he was aware of the changes that happened in France post-1934. My second core proposition is that, hey, at the end of the day, these are choices made certainly by a giant of mechanics, but this was 100 years ago. And, you know, we are very much in position to challenge such choices. If the aim is to elevate education in a field that I think, if you look at our peer subjects, fluid mechanics, rigid body dynamics, and so on, controls theory, that are not subject to the same sort of inertia of such a heavy history. I believe they're taught at a higher level, but that people may or may not agree with me on this. So my proposal is clear by now, hopefully, to everyone. I think strength of materials ought to be taught using a theory of elasticity approach in 2020. That's the only way to elevate education in this field and going away from the inconsistencies of SOM. Now, this assumes, I do not mean for that to be a general rule. I mean, there are different programs in different places. But my understanding, and maybe wrong in this, is at least this is true in my institution, there is typically a three-course sequence in deformable bodies, starting with a general introduction in solid mechanics, and then there is this junior level structural mechanics course, followed by, we need to teach something that is centered around finite elements. I hate for it to be just finite elements. It needs to be variational principles, energy methods, and so on. But that's typically a three-course sequence that usually come after a course on statics, which itself comes after a general course in physics, where students get introduced to Newtonian mechanics, among other things. And so my focus is on this part here, structural mechanics. The tendency is to teach this 1 and 2 as strength of materials 1, strength of materials 2. And this is really a wasted opportunity, really. And doesn't prepare students well for finite element analysis, because when you solve a boundary value problem, you've got to know exactly how you're posing boundary conditions and so on and so forth. And strength of materials sometimes just brushes that completely, does not obey all governing equations and so on. So it makes the link even to an undergraduate course on finite elements very difficult, unless your focus is only on finite elements of beams, an approximation, approximate theory. And like I said, if you examine, for example, a lot of people who teach strength of materials are allergic to things such as differential operators. They don't want to talk about divergence of the stress or gradient of displacements or things like that, right? But in fluid mechanics, they talk about incompressibilities as divergence of velocity being 0 and the curl, this and that, the rotational flow and so on. There is a mismatch at the same level, right? Junior or sophomore. I also think that is this catastrophe of throwing logic away out of secondary education has caused a lot of problems with students. Sometimes I talk to them about necessity and sufficiency and these kind of things, and they seem lost. I cannot stress the importance of analysis. It's not enough One needs to supplement that with geometry, obviously. And I think that we have nowadays tools that maybe Grashoff and Winkler did not have at the time. I think scientific plotting is very important, and visualization plays a role in helping present this field at an elevated level. Of course, there are challenges, there will always be, but in the interest of time, I'm not going to discuss it in detail. I fully believe that the benefits outweigh the difficulties. And in closing, I think it's clear that structural mechanics and mechanics in general is a difficult subject. And it's not by, randomly picking subjects, what to teach and what not to teach based on what's simple for the student that we're going to elevate the field. I mean, didactics makes things more approachable and more accessible. It is also an old subject. Let's just face it. I mean, giants have stumbled on it. I mean, Euler, Coulomb, Navier, Cauchy. This is a field where analysis, for the most part, has always been ahead of experiments. Because a lot of people sometimes say, at the end of the day, this is just an approximate theory, and ultimately, we have to check with experiments. Experiments have stumbled big time on this, okay, historically. Two renowned physicists, Cornu and Wertheim, got it all wrong. I mean, after all, the reason why Navier and others have believed that plane sections remain plane and rigid is because the measurements of Wertheim and Cornu seem to confirm that they remain rigid and planar under general bending or torsion. Okay, but they were not accurate. And I cannot but quote Josiah Gibbs here. I mean, again, emphasizing the role of analysis and theoretical investigation, that it is the office of theoretical investigation to give the form in which the results of experiments may be expressed. They go together. And the way we interpret many of what we consider as trivial and basic experiments, they are interpreted on the basis of prior theory. And thanks to Saint-Venant, we have come a long way, I think. Now, of course, the utilitarian teacher may say, okay, at the end of the day, save for a few formulas that clearly are not there in SOM books, on the essential parts, the final equations are the same, and so it's what you do with them. Of course, this is very important. And they may say, just the skill is what matters. I leave it up to people to decide how to manage the balance between utilitarian versus fundamental, what they call cultural oriented teaching. And finally, since I started with a pond and finished with one, so if you believe that it is not possible to teach SOM in a different way and is effectively possible, then you must really think that Timoshenko killed structural mechanics. And with that, I will stop.
Thank you, Amin. You have made your case. Now I leave it to the jury. So we invite questions from the audience. You can put your questions in the Q&A box at the bottom. You can put it on the chat box as well. I already have a question in the chat box from Arkady Daiskin. Euler-Bernoulli theory is to produce the main term of asymptotic of small beam thickness. All assumptions go to this effect. So you cannot relax one assumption and leave the other untouched. You may need to relax all of them. I can check if he's there. Then maybe he can ask the question.
I think I may not have made the point clear enough, but the point is a logical one. The Euler-Bernoulli theory arrives at the critical result, an important result, the curvature moment equation, starting from a set of assumptions. Okay? The point is that the student is left with the idea that these assumptions are essential to arriving to the final result. The exercise I went through is to show you that they are not. We know, I didn't go through this, but it's the student may be familiar with the Saint-Venant solution to that. The exact solution shows that there is warping and that the cross sections deform. Yet, that equation, at least for cantilever beam, is exactly valid. And then if you study it in detail, when you show that the deflection due to shear is negligible for sufficiently slender elements, it does remain valid in spite of the cross sections not remaining plane upon deformation and being rigid. So when I was relaxing one or the other, it was a mere logical exercise. That's all. But the key point is that you can arrive at the same result from a theory of elasticity approach. It will give you that and much more, and show you under what conditions they can rigorously, the cross sections remain plane or not. In fact, we know. The contention with that theory is that it assumes, back at the time of Navier, it was okay to make such assumptions because presumably either you didn't know, it was an approximation. But no, today, we know exactly when these things remain plane, that is pure bending of any cross-section shape. And we know exactly when they do not, that is every other case. So what's the point of assuming something we know is wrong?
Yeah, Simon Eugster has a question. Simon, I have allowed you to speak. You can ask the question to Amin directly.
Yes, I hope you can hear me.
Sure.
Absolutely. So thank you very much for the talk. It was really encouraging to think a little bit differently about strength of materials. And I absolutely agree with you that an education in elasticity theory before tackling the structural element problems is relevant for a good education for students, because most of the problems nowadays are more involved with elasticity theory, and that's where it is headed. I just wanted to ask you, which is the most modern source where you find the Saint-Venant problems?
Well, most modern.
Or which is a good source where you can
for what case? Because the problem of torsion is rather well described in a variety of books, including, so Timoshenko has, of course, a theory of elasticity book with Goodyear, in which it is presented in a nice way. But you'll find it in some of the books I've listed here, Craig and Bouchot and Maxon and so on and so forth. But the case of bending is not presented in many places. By the way, should say that the reason I've been thinking a lot about this is I'm writing a book about structural mechanics, and so I'll be more than happy to share that when it's in print. And I've been teaching from it last year and this year as well. In fact, even on torsion, I would not present the Saint-Venant theory the way it's presented in Timoshenko's book or any other book, the so-called semi-inverse method. This semi-inverse method is has a very interesting historical value, because it is legitimate, in epistemologically speaking, to ask the question, how did the person come to think about what they have developed and so on and so forth? But, research is noisy, and not every noisy character of research is worth documenting in a teaching environment, especially to undergraduates. And so the way I teach it is basically by using stress functions rather than displacement formulations and so on. And, and so I would say, in short, there are a variety of elasticity books in which you're going to find a good coverage of the subject, both for torsion and bending, including Timoshenko's book. You'll find it in a variety of other texts. The bending, not much so, except in graduate standing books. And I think the challenge is how to make this more accessible to undergraduates is the issue. And that I think takes a lot of effort in illustrations, in didactics, in simplifying things, in using the simplest notation possible, and so on and so forth. And then hopefully when my book is complete, it will address some of these aspects.
Okay, thank you very much. I'm looking forward to see your book then.
Yeah, I mean, Amit Singh has a question. Amit, so it's basically a question about why shouldn't we just teach elasticity, jump onto continuum mechanics? Why worry about SOM at all? So Amit, you can go ahead and ask your question. Amit, are you there?
Yeah, can you hear me, please?
Yeah,
yes,
we can hear you.
Yeah, so thanks for this wonderful lecture. Actually, I learned a lot. My question is that nowadays there are so much good softwares available. Why don't we simply teach with theory of elasticity to second year or third year undergrad students, and then simply at the end of the in fourth year we teach continuum mechanics? So just get rid of all these structural mechanics with beam theory, etc., and keep this as a simple example problems. So what is your take on this? Thanks for it.
no, I think this is probably a trend that may have occurred here and there, but I wouldn't agree to this. You know, I'm exclusively talking about engineering programs, okay? And whether you're talking about civil, mechanical, or aerospace engineers, I mean, structural analysis is important. So structural mechanics is a subfield of solid mechanics, which itself is a subfield of continuum mechanics. And when I may have mentioned this to me, before you teach structural mechanics with a theory of elasticity approach, that's the premise. Obviously, you can't be covering all the subjects of this: axial load, bending, simple torsion, general bending with shear, some elements of statics and geometry, and then combined loading and buckling. I think stability is important. While providing for the first time an introduction to the governing equation of theory of elasticity. Of course, a review at the beginning is useful. So that can only be built on a previous course that is a general introduction to solid mechanics. That, to me, means an undergraduate version of continuum mechanics. What else? But it should not be something too difficult. I mean, continuum mechanics is common to solid and fluid mechanics. And so it has to be in solid mechanics. And then, to actually be able to solve any type of problems, you need a constitutive relation. And so to me, when I say an introduction to theory of elasticity implies that you're touching upon key concepts in continuum mechanics for solids, but simply focusing on, linear kinematics, linear behavior, elasticity. If that is done properly in these courses, then you can imagine that for the most advanced students, offering a more advanced course as a tech elective in the fourth year or the final year. But even if that were not to happen, those students who are interested in graduate school, they will be fully equipped to get into hardcore continuum mechanics and other related subjects, because right now it's really a step function, at least in the US, from undergraduate education that is ingrained in SOM to continuum mechanics. It's too much for them to. And my interest is genuinely in undergraduate education here, and so me emphasizing structural mechanics does not mean not introducing continuum mechanics, but in the simplest way possible, which I would call an intro to solid mechanics, general governing equation, introduction of stress and strain. In a way, many books do, but I find it amazing that some SOM books don't even contain in 500 pages a single statement of stress equilibrium. Stress equilibrium. And no wonder they don't do that. You can, I reckon that you can teach SOM without even talking about the stress, really. That's how the field has historically started. I've been designing things for 500 years, if not longer, right? Based on some science. And but some books don't have stress equilibrium. It's really a drastic didactic choice. I would like for these governing equations to be introduced in early course, where without a focus on beams and stuff. I mean, you can use beams, just like you said, as an example. You can use pressure vessels, whatever, to illustrate key things. I think, notion of stress and equilibrium, notion of strain and kinematics, linear isotropic homogeneous elasticity, just get students familiar with Hooke's law and massage it in different ways, and then boundary conditions. And for that, you need to solve simple problems and exercise their minds on such problems. And of course, it is tough, right? Because it's a dry subject. You need to make it interesting by, serious effort in visualization. But that will prepare them to structures where that ought to be focused on relatively simple structural elements. And of course, can have courses on plates and shells and so on at higher levels. Beams exemplify everything you want to convey to students, and are arguably the most important in practice, in engineering practice.
Isaac Elishakov, he has quite a few questions. So Isaac, if you can come in and ask them to Amin yourself. Yeah, Isaac, you have to unmute yourself and ask the question. Okay, he seems to be having a problem because he has raised his hand, but he's not speaking. So I will ask his questions, few of his questions. He says in his biography, Timoshenko mentions that the center of gravity moved to Germany, and in France, no breakthrough research was done. That's his first question. And the second, well, it's not a question, it's a statement. And the second one is in 1979 at Delft University of Technology, they taught a particular case of a statics course in pretty much the way Amin has described. And from 200 students, only 7 passed. Yeah, that's it.
Yeah. I mean, on the first question, I do not know what is meant by the center of gravity moving to Germany means, and what researchers he has in mind, maybe Brecht, I don't know, or Klebscher. But there's it's an osmosis. To me, really, the field of structural mechanics, between the contributions of Saint-Venant and those of Bresse, you have it all. Anything else, in the context of beams, is peripheral. And interesting, examinations of details here and there, Vlasov's, there's for non-uniform torsion, and so on and so forth. To me, these are homework problems. Well, on the second question, the 1979 experience, I know that Delft is one of the good places where I'm not surprised that some attempts of this sort have been done. Let me tell you 2 things. I did mention the year 1934, where Gaston Pigeot, who was a professor then at École des Ponts, someone who was of the same opinions as Bresse in teaching strength of materials the traditional way, very vehemently in his editions of 1920 and prior to that, just said there is no need to do theory of elasticity approach and so on. Completely switched for reasons similar to those I've elaborated here. it is not satisfying for the mind to be invoking fallacies, really, in justifying formulas simply because they're useful and they're true at the end. And so since 1934, essentially without discontinuation, this subject has been taught at École des Ponts, and we're talking about 100 years now. And Timoshenko ought to know better using this approach. I happen to have been to Supaéro. I was admitted to École des Ponts back in 1992, but I decided to go to an aerospace engineering school. Supaéro was founded in 1909, and they have adopted exactly what the temple at the time of structural mechanics was, École des Ponts. And so the program has been exactly the same thing after a couple of editions of traditional SOM. So I have been taught that subject. I must confess that I have never learned SOM. I had to do a lot of research to be able to do this. I have never learned strength of materials the way Timoshenko or other standard books teach it. I've only been taught structural mechanics with a theory of elasticity approach. As for how challenging this may be and 17 passing students out of 200 and so on, I do not question the data, although I think some studies would be legitimate. What I would tell you is, because of my sheer ignorance of both the English literature on the subject about 17 years ago when I came to A&M, and because of my background, when I came here, first semester, I taught structural mechanics the way I thought it should be taught. So I have been teaching this subject for 17 years at A&M, getting anywhere between 60 to 90 students per edition. I have calibrated a little bit after the first semester to the average math level of my students. But, I do not claim that I get the best student evaluations out there, but I think they are right there in the decent. And that is if you assume that this is the only measure by which you, and I do not pass 9 out of, I think it's the other way around. I think if 9 must be the maximum number of students not passing my class out of 100. 17 years of teaching this. So that's why I said it is a challenge. It is very easy to screw it up. But, and this is why I think there needs, and this is a collective effort, right? We need resources for this. We need resources. We need not just resources for students, but resources for instructors. Because a lot of things have been unlearned. We need to learn again how to teach the subject.
Shailendra Joshi has a question. Shailendra, you can ask it yourself.
Thanks, Sumit.
Hi.
A wonderful talk. I think very thought-provoking. I had a couple of comments and then a couple of questions. First, I think your point of comparing solid mechanics with fluid mechanics, the way things are taught, invoking concepts of vectors and divergences and curls, I think it's very well taken. Those ought to be brought into the core structure of solid mechanics as well as we teach. At U of H, actually, we have made this conscious effort to go in that direction. One of the slightly selfish motives over there has been that the number of students, undergraduate students, who end up doing internships and research studies through fluid mechanics is much greater than the students who move into solid mechanics at the undergraduate level during summer, for example, simply because they find it more exciting to work with fluid mechanics principles. And I think your point was absolutely point on over there. So slightly more contentious arguments are, you mentioned about teaching being didactic, right? Giving details and, but the core question that I have is, while teaching, one has to be careful going from didactic approach to a pedantic approach. Now, there's a very fine line between that. How do you address that issue? That's one question. And the second question is slightly more simpler, I think. The way you structured your talk, it seems like you're trying to take a top-down approach, going from, for the particular problem of Bernoulli-Euler and Timoshenko and Saint-Venant, you're trying to say that let's think of Saint-Venant as the core approach, and then deduce Bernoulli-Euler or Timoshenko as degenerate cases of that. Is that fair way to assess it?
Let's start with the easy question, which is the second one. No, the answer is no, because after you teach a Saint-Venant approach to any problem, why in the world do you want to talk about Euler, Bernoulli, or Timoshenko?
Mm-hmm.
To me, but for Timoshenko, it basically is not taught much anyways in books. It's maybe important in some vibration problems. But to me, Euler, Bernoulli is a homework problem, maybe 2 homework problems. Okay? But
Mm-hmm.
once you have taught the approach from the theory of velocity, and you arrive at the key conclusions that if you are in pure bending, then plane sections remain plane, and the deflection is given by, the curvature is given by that equation, you have achieved what the other alternative fallacious way obtains. So why would I even dwell on it? I think from a historical perspective, it's interesting. So that's why I put it in a homework problem, you know? But I don't deduce. Why do I have to deduce? You know, you have a theory that's exact. It produces results, some of which encompass what the approximate theories seem to be proving, which it's not really correct proof. There's no need to dwell into that. It would be a total waste of time. I must confess that I didn't fully get your first question, Shailendra, about didactic versus pedantic. I mean, can you elaborate a little bit more on that?
It's a question of, you know, what level of detail you want to present. You mentioned about, you know, the value of teaching a course or writing a paper as a story, right? I think some of the finest examples of writing, you know, expressing any ideas as a story come from simplicity. And elegance may not always, well, in many cases, simple ideas are more elegant to express. And you can actually take a number of examples from, from around us, from nature, from things that we see around, and they can be expressed in a very nice form. And the moment you bring a significant amount of complicated theory associated with it, things start to become less physically based and more abstract.
Yeah, but let me take issue with this. I mean, there is no complicated theory. Like I said, there is a theory of velocity.
Mm-hmm.
There is a philosophy in which theory of velocity is treated as a distant, magical thing that you only invoke sporadically in a book or a course when you're stuck. And you say, well, in these cases, these formulas do not work. But we know from theory of velocity that the cross-section actually warp, and either you diminish that or you mention some errors. My question is that true empowerment of students? I mean, how different is that from vulgarization? From basically just having students admit things. To me, in order to measure errors, you need to know what the reference is, to know enough about it. And it's okay if we have collectively reached the wisdom that such a reference is not accessible to students. And that we have just to show them a bunch of formulas here and there, and because these formulas are what they use, and try to develop another sort of intelligence that is just, in terms of systems thinking and so on and so forth. It's perfectly okay. I just think that this is okay in programs where there is more of a practical twist to the education, where they cannot afford more than a course because they have many other things. Then I think really this is what's needed. But I think if you can afford this 3-course sequence, typically what happens is people do it twice. One at sort of elementary, the other one is doubling the thing. But the theory of elasticity is challenging, but people need to be introduced to the concept. And we are discussing those concepts all the time. Drawing an FBD is a tool to establishing equilibrium. Equilibrium is important, kinematic is important, and you have to explain to them very early on and hammer this every time that constitutive relations are needed for these problems and why they are needed. And boundary conditions matter. And then you pose the problem. The 7-0 problem is very simple, right? It's a prism. It's a prism, for God's sake. And the only thing is you have distributed tractions on both ends in a way that may result in a bending moment, in a torque, or in a tensile or compressive force. And you ask, okay, what can we extract, the gist of it, right? You solve the problem. That's the technically difficult part. And the thing is, you see, I spend, for example, 2 hours, that is 2 sessions, on presenting Saint-Venant torsion theory or Saint-Venant bending theory. But these are 2 hours spent in tackling a double infinity of problems. Compare this with, I think, 1.5 hours, almost 2 hours also, in developing the simple SOM approach to torsion or bending with shear, with all sorts of not so easy drawing to make on the boards. We have to do PowerPoint or something like that. But to arrive to a much, much narrower result. So you tell me what simplicity is. Explaining a double infinity of solutions or a narrow one, and then you go and extrapolate from there and have students admit many results that you have really not empowered them with appreciating. Yes, students are not all of them going to, they're going to struggle. They should struggle. This is not an easy field, right? But I'm not going to either give them homework on Saint-Venant solutions, nor am I going to test them on that. It's just a way of establishing key results. And I am full believer of training students on solving problems with the end equations we established. Like I said at the beginning, this critique is not of the end results that are typically obtained in strength of materials, but in the way they are obtained. Because in the way we're obtaining them, we're framing the minds of people. And so ultimately, from a purely utilitarian point of view, I think I achieve all the above, all of what my colleagues who want to teach it the traditional way achieve. Because I solve just as many problems, if not more difficult ones, more thorough ones, more complete ones. They do the transverse shear of multi-cell sections and the like. But in establishing the equations, they waste no time in using quasi-proofs. That's it. And by doing so, I think I prepare the students better for the follow-up course, because if they know how to pose a boundary value problem and they have reflected on the type of boundary conditions they apply in something they tackle analytically, and they realize how difficult it is, they will all the more understand the power of numerics and also how to pose properly a boundary problem that is to be solved numerically.
There's one more question from an anonymous attendee. Are you game for it? Are you too tired? It's a simple question. When will your book be available?
Yeah, so, I was planning to be on sabbatical this year to finalize it. And then COVID hit, and I'm teaching the semester, so sort of getting more feedback from students. We shall see, because having spent almost a full year last year working on that, the research enterprise takes a hit, and has to be balanced. But hopefully, I would say in a year or so.
Okay, there are no more questions, at least not ones that I can see. Thank you very much for accepting our invitation, giving this excellent talk on something that is very different from what the other speakers are talking on. This was very timely, and appreciated. So we can't clap. So I will just clap for the others. Thank you very much.
Thank you, Sumit, for having me.
Yeah, thanks a lot. So we'll close the meeting.